Hello everyone, my name is Vladimir Nikolic and I'm a research programmer at the Bureau Lab at Canada's Michael Smith Genome Science Centre. Today I'll be presenting on ABySS 2.5, which is the latest version of our short-read de novo genome assembler. And in particular, this version introduces sufficient repeat resolution, which is used to improve assembly quality. It has been about 12 years since the initial publication of the ABySS assembler and about 4 since its successor, ABySS 2. In the initial release, the Bruin graph data structure, which is used for assembly, was distributed across multiple machines. And the idea here was to aggregate the memory of these machines, which was at the time required to assemble large genomes such as Homo sapiens. Now, this model required inter-machine communication, which has extra overhead and requires infrastructure. So you would want high-speed connection between these machines in order for them to work efficiently. And this motivated the design of ABySS 2. Now, ABySS 2 employed the Bloom filter data structure, which is very, very memory efficient. And this decreased memory usage up to 10-fold. Now, with this low memory footprint, we were now able to assemble large genomes on a single machine, even on commodity hardware. And here, because we're assembling on a single machine, a multi-threaded model was used instead of distributed computing. In the latest release of ABySS, in ABySS 2.5, we've focused on improving assembly quality. And here we've introduced a repeat resolution algorithm resolver. This algorithm tries to sort of untangle situations such as these here in the assembly graph. So you have a green repeat and neighboring nodes, and you have a window that is close to read size that sort of tries to find paths. This algorithm follows the footsteps of ABySS 2 and uses a Bloom filter in order to minimize memory usage. To demonstrate the improvement in assembly quality, we have taken 4 human data sets, 2 of 150 base pair paired end reads and 2 of 250 base pair reads. These were assembled with ABySS 2.0 and ABySS 2.5. And on the y-axis, you have contiguity in NGA50, and on the x-axis, percentage of complete BUSCO genes recovered. And these are both metrics for evaluating assembly quality. And you can see that in each of the data sets, assembly quality improves. So the circle is the 2.0 version and the triangle would be the 2.5. And you can see that on both metrics, ABySS 2.5 improves the assembly. And further, we showed the download counts for the ABySS assembler over time. So this y-axis shows the cumulative downloads of the assembler, and you can see that in 2021 we still have sort of steady increase of downloads, and this sort of demonstrates that the tool is relevant even now, more than a decade later. A little bit about the repeat resolution algorithm. So the resolver algorithm uses the short-read range information to find paths in the assembly graph. Currently, the Bruin graphs have nodes that are shorter than the read size, and so there's some information that's left unused, and that's the point of the resolver algorithm, to sort of recover this information. So if you have this repeat here, and you have 2 reads that belong to 2 distinct paths in the graph, resolver would be able to identify where they belong and sort of duplicate this repeat and then connect it to the corresponding graph nodes. And you have the resulting simplified graph here. And this helps any further algorithms downstream that try to improve the assembly graph further, because now we have a graph that's easier to navigate. And so in conclusion, from the initial release to ABySS 2.0 and now ABySS 2.5, the assembler has come a long way in delivering high quality de novo genome assemblies, and it is very good on memory usage. And the latest addition to the ABySS pipeline, the resolver algorithm, further improves assembly quality and still keeps the resource usage low. This work was funded by Genome Canada, Genome British Columbia, National Institutes of Health, and Canadian Institutes of Health Research. Thank you for listening, and I would invite you to also check out the posters of my lab mates, Lauren Coombe, Janet Lee, Daniel Lin, and Renee Warren.